Hello, everyone, and welcome to All Space Considered. It is, well, tonight it's not actually the third Thursday of the month. We are filming this episode of All Space Considered in front of a live studio audience, and we're going to broadcast it later. So we'll broadcast it in about a week. So if some massive astronomical discovery happens in the next week, well, there's a reason we're not talking about it. But tonight we have a really great show, and we're coming to you from the Boeing Education Center at Griffith Observatory. We're not in the Leonard Nimoy Event Horizon Theater tonight because it's being renovated. We have some new projectors coming, some new stuff, and when we're back in there, well, you're going to notice the difference. It's going to be really great. But tonight, we have a great show. And, of course, All Space Considered is brought to you by Griffith Observatory, the City of Los Angeles, and the Department of Recreation and Parks. And, as always, we like to thank our exclusive nonprofit partner, Griffith Observatory Foundation, for all the support they provide. Well, tonight, we are talking about, of course, space. And I have some wonderful folks with me tonight. I have Laura May with me and Jared Head, and they've joined me tonight to talk about some fun stuff. And what we're going to do is I'm going to do a quick astronomy news bulletin to start the show, and then Jared's going to do an out to launch, and then we're going to talk about whether JWST has broken cosmology or not. So maybe it has, maybe it hasn't. I don't know. We're still here, though. So the universe did get here somehow. So we'll talk about that. Well, first of all, what is this wonderful image that's been in the background? This is actually an image of some colliding galaxies, believe it or not. So this is a JWST image, and here is the image they released. And this is how they released it. And it's actually known as the penguin and the egg, which is kind of fun. And it does look a little like a penguin and an egg. And this was released in honor of JWST's second anniversary of doing science. So I decided the second anniversary is the cotton anniversary. You're supposed to give a cotton gift. So I gave JWST a cotton T-shirt. And yes, that is the Hubble Space Telescope on the T-shirt. So
big fan.
Big fan.
Big fan.
Exactly.
Big fan.
Well,
Big
why
fan.
wouldn't Webb be a big fan of the Hubble? Anyway, other things that have happened here, a lot of folks realized there was an earthquake just the other day. What night was that? That was Tuesday night. I was sitting at home. I was working on All Space Considered, of course. All of a sudden started to hear these noises and some shaking. My dog looked up at me. He wandered away. I thought, what's going on? It was a 5.2 magnitude earthquake. And it was, well, not too far from Bakersfield, actually. And the cool thing about it was, of course, we have a seismograph here at Griffith Observatory. And here it is actually doing its thing. Sorry about it, it's a little shaky here, but you can see the needle going back and forth. And it is indeed drawing a line on there. And here is the pen, the actual markings on that roll. So we measured the earthquake. It was pretty much pegged. It was as much as it could go side to side. You can see we maxed it out. And we caught a lot of aftershocks, too. There were many, many, many aftershocks. So it's a lot of fun. Griffith Observatory is one of the few places an earthquake hits, and people run into the basement. They go down to the bottom of the building because we want to see the seismograph going off.
That's
so
exactly what I did.
It's a lot of fun. Well, exactly. You got the
Before
video.
going under my desk, I thought, I need to call work and see what's on the seismograph.
Exactly. It's a lot of fun. Well, some other things have been announced, too. This is an image of Enceladus and those plumes. Enceladus is a moon of Saturn that we know has liquid water down under the surface that somehow escapes in sort of these geyser-like plumes. Well, that means it is a candidate for life. Maybe there's microorganisms down in there. We're not sure. This is Europa. Europa also has some geysers or plume-like things that are coming off it. They're not quite as obvious as the Enceladus ones, but we believe there is a liquid ocean down in there. In fact, with Enceladus, we think probably what's super cool about it is the fact, with Europa, what's cool about it is the fact that that ocean is in contact with the rock down below, and that rock might be molten, which gives a heat source. You can have vents down in there, a heat source to create life. Just like in the bottom of the Earth's ocean, we have those black smoker vents. Those are sites of lots and lots of biological activity. So maybe there could be life down in the ocean there. This is the example of your Enceladus, how it might be working. There's a little salty sea down in there, but that sea has to work its way through a thick layer of ice, but still a candidate for maybe life down in there. Now, the new study is some folks wanted to know, could we still see signs of life on the surface? Those plumes are shooting stuff from down below. It lands on the surface, and the sun blasts it with ultraviolet radiation. It gets cosmic rays, so it's hit by this harsh radiation. So they decided they'd take some amino acids and freeze them and then hammer them with UV radiation and strong radiation and see, do they survive in that state? And the answer is yeah. A whole bunch of amino acids still survived. In fact, they survived better when they were in pure frozen water, which a lot of the Enceladus stuff is water there, and Europa is water. However, if there were silicates and particulates mixed in, sand essentially, they didn't last quite as long. So it might be important for the Europa Clipper mission to be able to go there and find areas that have good vibes only. Well, what I mean by that is really that it has a lack of silica. You're going to want to go there and find parts of the surface that have less of that sand and more of the pure ice to see if we can find the signs of life that are left over on the surface there. So that Europa Clipper mission is going to launch in just, well, it's supposed to launch in October, but they were having some problems. So we'll see whether they actually are able to launch. But we have Bob Poplardo, one of the mission scientists, will come talk to us in November to tell us all about it. And I'm going to ask him if this new result, if they're excited about that, and if they're going to be looking for places to land. So stay tuned for that. Right now, the sun has been incredibly active. I don't know if you've noticed, but this is an image of the sun. This is a real picture. And there have been a ton of sunspots. In fact, this is on August 1st. I'm going to step them through it, and you can kind of see them rotate. 3rd, 4th, 5th, 6th, 7th, and then this should be today's. Indeed, this was today's sun. And there's just a ridiculous number of sunspots. In fact, here's the plot of the number of sunspots versus time, and you can see we have hit a high that's been more sunspots than in what, 24 years?
23 years,
23 years.
Yeah.
So really crazy. In fact, this is the day that we hit the maximum on July 18th. Doesn't look quite as spotted as today's sun, but there's many more small spots on this sun than on the other one. Now, what's cool about this is normal for the sun. The sun goes through this sunspot cycle where it gets lots of spots, then very few spots, and it's every 11 years about you get one of these peaks. Now, the actual cycle is a 22-year cycle because the magnetic field flips. So what you're seeing on the left, what you're seeing up above is a graph of where those sunspots occur. They start at high latitude, move closer to the equator, and below is the count. And this is the magnetogram. And across the top is the North Pole, across the bottom is the South Pole, and blue and yellow are north and south magnetic poles. And you can see it flips. So as you go from the left to the right in time, you can see it first it's yellow on the top and blue, and then it's blue on the top and yellow on the bottom. That's that magnetic field flipping. And every time this happens, the sun gets super active. In fact, right now, the sun is just going off. These flares are popping off like crazy. You can see in this little movie here, this is a Solar Dynamics Observatory movie. It's a spacecraft that observes the sun in X-rays and really high energy light. And it's seeing these flares go off. Anytime you're seeing that bright flash, that's known as a flare. Now, flares are also associated with coronal mass ejections. This is a flare, and you'll see that material gets blown completely off of the sun. It leaves it. Let's zoom in on it a little bit here. So this was a really strong flare that just happened, and this is the size of the Earth compared to that. So this is much bigger than the entire Earth. This is crazy large. This is a giant, well, first a prominence, and then it becomes a coronal mass ejection when that flare hits. Now, what does it look like when you back away? This is a view from the SOHO spacecraft, and which is the Solar Observatory Heliophysics Observatory, so something. Anyway, it's a European one, so you should know.
I should know this.
So anyway, put Laura May on the spot.
I don't know everything.
Don't know everything, but anyway, but I love this one because it gets you a further view. The sun is blocked by that disk in the middle, and you can see every time a flare happens, you get that burst of gas that comes off it. Those are coronal mass ejections. And when those hit the Earth, you get aurorae. So right now, we're back again in this time where they're saying we could have aurora events. The sun is so active right now. Keep an eye out for it. There could be alerts. Last time this happened, people saw them out in Mojave. They went out in the desert and with a cell phone, take a camera, take an extended picture, just 10, 15, 20 seconds long. People were picking up color. They weren't seeing color with the naked eye, but a little bit of extra glow. In dark sites, they were even seeing color if you went far enough north. So
I mean, I saw them up at Mount Wilson.
yeah,
So an hour from here, you could see them. You had to be above the cloud layer. You could see them a little bit with the naked eye. You could see the pillars. It's true
Yeah.
that the colors were not quite as visible. There was a little pink, but the pillars are certainly visible. So
yeah. So if there's an announcement that there's going to be aurora, get out there and see them. So amazing stuff. Another study that came out that I was really interested in was this is an image that contains both galaxies that are in clusters. The pink is X-ray light. The blue, come on in. The blue is actually a measurement of the dark matter in the cluster. And what you're seeing here is two clusters that passed through one another, and the gas shocked in the middle. So the gas that was around these galaxies ran into itself, got stuck in the middle. The galaxies passed through one another, but the dark matter led the whole show. They were out in front, which is kind of weird. Let me show you a simulation. Maybe I need to click it. Maybe it's the next. There it goes. Perfect. So the simulation, the two clusters are coming together with gas. The dark matter gets pulled out in front. That's the blue. The gas gets left behind. So actually what you see is the blue in the further edge, the white, which represents the galaxies, is kind of in the middle, and or a little further out in the very center is the hot gas that shocked against itself. Why did this happen? Why did the dark matter flow faster than the galaxies? This is the first time we've ever seen this. We've seen before in things like the bullet cluster, where the galaxies went through one another and the gas shocked in the middle and the dark matter traveled with the galaxies. But here, the dark matter was faster than everybody. They are thinking it has to do with electric and magnetic forces. So magnetic fields and electric fields actually slowing down the physical matter. So this is a weird thing, that dark matter is flowing faster than the galaxies are. First time we're seeing it. So a very, very cool result. I don't know how it's in here twice, but let's watch it one more time because it's neat.
It's beautiful.
So the blue is leading,
Oh,
and the dark matter passes through. The galaxies pass through one another, and then the gas hits itself and is left in the middle. This was actually measured in a galaxy cluster. They've measured this with a whole bunch of observatories. They used Keck, they used Chandra, they used Hubble. So they've used a bunch of different ones to piece this together. But this might tell us a little bit of something of what's going on maybe in the early universe. If dark matter can flow at a different rate and clump differently than the visible matter and behave differently than we thought, we need to include that in our models. So anyway, that's our little astronomy news bulletin for tonight. So now it's time to turn to Jared. And I've got a question for you, Jared.
Yes.
Did you see this thing?
I personally didn't get to see this specifically, but this is
Let's see if it loads.
this is a upper stage from a Chinese Long March 6 rocket. What we thought was venting its propellant overboard, as seen from Europe, I believe. But now we are in a little bit of a question about what this is, because just a couple hours ago we confirmed through ground-based radar that actually this upper stage of this Long March 6 rocket has had a nice way to put it would be a fragmentation event. So yeah, go ahead.
Sorry.
Yeah, no.
Uh-oh.
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 Mic fix. Mic check.
You did too much choreography in between.
Sorry.
Got to slow your dance moves.
Yeah.
So on top of it, this was supposed to launch, or be the first launch of a constellation of satellites that they have. So this is the Chinese joining SpaceX with Starlink. Amazon has a planned constellation. Other folks have planned constellations. So what this means is more satellites in orbit. Lots more. They were going to launch probably thousands in this constellation eventually. So, but it blew up, you're telling me.
Well, the upper stage has fragmented, and I think it's somewhere at about 700 to 900 pieces at a orbital altitude that's high enough that these pieces would take several decades to come down. So this is a really not great thing to happen. This is also 2 for 2 on the upper stages for Long March 6s, because back in 2022, when they had the debut of the Long March 6, its upper stage also fragmented shortly after launch as well. So right now, I mean, this is literally hours old as we're filming this. It was confirmed about 4 hours ago. So we're still even trying to figure out what is going to be the low and the high points of the debris coming from this. We don't even have that yet. We just have a general idea as to what altitude it occurred at, but we're going to have to pay some very big attention to that over the next couple of days.
Yeah, so this isn't just your average jellyfish.
No, not your average jellyfish, which we'll talk about some
Yeah.
jellyfish in just a little bit, if y'all are big fans of jellyfish like I am.
Yeah.
So, but we have had a lot over the past couple of months since I last did an out to launch, and probably the biggest one was SpaceX with their Starship Super Heavy test flights and continuing that regime that they're working within and trying to speed up the development of the largest rocket in the world, 17 million pounds of thrust at liftoff, which is essentially a little over twice a Saturn V. This rocket's over 400 feet tall. It's basically, if you want to say like biggest, this is a good one to start at with what we have right now. That first stage runs on 33 Raptor engines, and they did lose one on this flight, which was the fourth and most recent flight that they had. They do a special technique called hot staging, where they actually will ignite the second stage engines while it is still attached to the upper stage and then separate the upper stage. This adds a little extra efficiency towards the amount of weight that you can get to orbit. And then they also have a portion of the lower stage, first stage, excuse me, called Super Heavy separate. And the whole idea is that they are going to take Super Heavy and land it and reuse it, and then the spacecraft portion, Starship, will also do that. By the way, this is about 250 feet tall, in case you're wondering how big this rocket stage is. Wow. It's absolutely massive. So to see it coming in like this and touching down in the Gulf of Mexico with everybody at SpaceX headquarters in Hawthorne, very excited. This was a real treat to get to watch this live. But of course, it's not just Super Heavy. We got to deal with Starship as well, making it to orbit and doing some of the things that it wanted to do in orbit, such as open its payload bay door and close it, which it did, and then go through atmospheric reentry. So this is a tile system that SpaceX has developed themselves, and this is one of the first times that we were able to actually watch the plasma of reentry in real time. And this is also material being destroyed by that plasma as well. But it was able to survive miraculously through that. See, that is not particularly great.
No, well, that reminded me of, what was it, was it the Challenger disaster?
Columbia
Disaster.
That broke apart on reentry, yes.
Yeah, it had a wing problem like that, a strike on the wing with the foam, and it burned through the wing in a similar fashion, but we were watching it live with this one. Only this one made it. It
yes, I was about to say, it shredded the aero surfaces on the vehicle, but the vehicle was still able to make it through atmospheric entry and land just about 6 kilometers off target from where they wanted it to be at. And as you saw in that little video right there, Flight 5, which they are now quickly approaching. All they have to do now is get the FAA regulatory approval for that. And the reason that the approval is having to occur and taking so much time is because they are planning to do this with it, which is that they are no longer going to be flying the Super Heavy booster to land somewhere in the Gulf of Mexico. They're actually going to fly it back to the launch site, and they're going to catch it with a system that they're calling the chopsticks. So they're literally going to hopefully precisely take the Super Heavy booster and land it right at just the right speed at the right time, right as these chopsticks come on, and catch it on those grid fins that you see right there. So either this is going to be one of the most spectacular leaps in rocketry technology that we've ever gotten to witness, or this will be one of the fastest ways a company has ever demolished a launch pad in order to make a new one. So, but we're going to find out probably, I would imagine, around mid-September in there to work with that. So, but very, very exciting with that there. I'm so excited I just can't keep my mic on with it there. So
it's pretty incredible.
Yeah, it is.
Is there a failure potential? Is there a rate that's, in terms of the percentage of what's the estimated failure rate?
Well, those are numbers that don't get handed out publicly, as you can imagine. I would hope that they're probably wanting that to be 0 at this point, but they are very far along in building a second launch tower at Starbase in Texas. So I would imagine that if this does end up demolishing their orbital launch platform or tower that they have here, that second one is pretty far along. So hopefully we won't have to wait too long for them there. I mean, after all, Flight 1, when they said, no, we don't actually need a water system to dampen the acoustics because 60 years of rocket design can most certainly be ignored. We all know that it took a little bit of time for them to rebuild the pad after all the damage that ignoring all that design did, but they were able to do it relatively quickly. So it only took about 4 months for them to rebuild the pad, that is really fast in this world. So
It seems like quite a leap to go from landing on, this movable platform that they have on water to just on ground with bare chopsticks.
oh, yes, it is absolutely ridiculous in terms of what they're attempting to do here. And this is all about rapid reusability. They want to be able to take these boosters and not just fly it like once a week. They want to be able to take a booster like this and fly it multiple times a day. So take that as you will. I've seen renderings of actually having the Starship vehicle come in and then land on top of the Super Heavy booster as well. So like the whole thing just lands on top of itself because, again, the Starship vehicle is designed to be reusable as well. But we'll have to see about that one. I'm not so gung-ho about that initially, but whatever happens, it's going to be interesting, and you're going to want to tune in for sure with it. So I will get up to watch that one. That's for sure. So yes.
I just want to know, are they catching that with the chopsticks mid-air the way it looks?
Yeah.
Yeah, pretty much. Yeah, those chopsticks can lower and raise and lower because the chopsticks are what they use to actually put the Super Heavy booster onto the orbital launch mount there. But yeah, that's about what they're planning to do with it there. So yeah, it'll be, again, tune in. It's going to be interesting either way it goes. So as the company said in a lot of their press releases, excitement guaranteed. So,
Exactly.
It's a good tagline.
so, yeah. And this wasn't sort of the only new rocket that we're watching. We also had Europe with their Ariane 6. Yep, represent, Laura, man, with that there Ariane 6, which is taking over in the legacy of the Ariane rockets. I mean, Ariane 1 all the way through Ariane 5. Just an incredible family of rockets. But this one is supposed to lower costs, make things a lot easier for getting access into space. I think it's very interesting that Ariane Space kind of takes a little bit of a different approach to their design and test as opposed to something like SpaceX. And Laura, you and I were actually kind of talking about that before because you are from France, so you like understand sort of the cultural differences that may be even in engineering with that there.
Yeah, and Ariane is a big part of, our collective. I think all of, everyone here has, obviously there's the Apollo programs and all of NASA, and for us, Ariane, I grew up with that. In fact, my father texted me the other day to say, oh, Ariane 6 has launched successfully, etc. Obviously, it's a different approach because it's not. I think a lot of people want to compare it to SpaceX, but it's more comparable still to NASA because it is. Ariane is from a conglomerate of about 22 European countries, and so governments don't do things in the same way as a private industry, obviously. But I think it's a good. Again, the European Union, we do things a little differently to the U.S. We're a little bit, NASA is a obviously very safety inclined. Everyone who does aerospace is. But I think in Europe, we have a little more red tape. We're a little slower at getting things done. It's still fairly expensive because we're not reusing, obviously, and that's the same as if you could, I think it's more comparable, in fact, to the SLS. But, I think Ariane 6 has proven itself. It launched the Web, obviously. Not Ariane 6, but Ariane 5, I believe, launched the Web.
5. It was the contribution.
That's right. That's right.
Yeah. And that was also a design choice too, because in order to fold up Webb, the Ariane 5 was one of the largest payload fairings that was available. So it was really the only rocket that actually could launch Webb at that time. So.
But that's also what we were talking about regarding the health of the aerospace industry. And this conference I was at the other day was mentioning it. Right now, it's pretty unhealthy to have only SpaceX have this giant monopoly on things. And Europe, as you were mentioning, constellation satellites. Europe also wants to have constellation satellites going in the next probably decade or so. So it'll be interesting if they can become a little bit more competitive, because right now SpaceX, of course, blows them out of the water in terms of costs. But again, it's a different process, and it's somewhat seen as somewhat more reliable, although again, SpaceX has proven that they have so many more launches that they're kind of also super reliable. But I think it's a good testament to European, aerospace ingenuity and, you know, strong build and all of that. So it'll be exciting to see where it goes.
Yeah,
Yeah.
you're never going to see me complain about more rockets. I can tell you
Yeah.
that. That's for sure. So,
Right.
and also very important too, assured access for Europe specifically
Exactly.
to have that. So it's not. It's just like here in the United States. You know, we want to have multiple rockets because you have assured access
Yep.
in case something goes wrong with a rocket. You know, like Falcon 9 had their upper stage failure about a month ago, and then basically we stopped launching rockets here in the United States because really most of the rockets that get launched in the United States are SpaceX Falcon 9. So it was a very quiet couple of weeks with that there. But yeah, so very cool to see that happen. I love this photo right here, which was a
Dassault,
Dassault
Rafale.
Rafale.
Sorry,
no,
how do you pronounce that in English? Rafale?
I was gonna say Dassault Rafale.
I
That's
think
how
they
was
say
gonna it. So
Dassault here in English, and I don't know how you pronounce the plane, Rafale.
I was just gonna
Rafale.
point to someone from the country that this fighter jet is from.
I've flown on. No, I'm kidding.
But this is heading on up. There are actually 3 of them that were chasing the Ariane 6 during launch on its way up. And then, of course, about 30 to 35 seconds after launch, the Ariane 6 just kind of left them behind. So.
Yeah, they lost.
Yeah, they
So,
lost.
Yeah, just a little bit there. But we do have something that's been in the news, not necessarily because of good things, and that is Boeing's Starliner vehicle, which has had a very shaky crewed test flight with this here. 2 astronauts, Butch Wilmore and Sonny Williams, flying up there, making it there, having some very significant issues with the thrusters in the service module, and now also, as revealed a couple days ago, also having software issues as well, such as not having software to run the capsule after undocking it without people on board. So, yeah, this is... Yeah.
Are they still trying to figure out what to do?
Yeah, they're still trying to figure out what to do. The idea is that it might take a month for that software to get written and then uploaded and things like that, and it's just really, really tough. So, anyways, how many of you have ever seen one of these before? Anybody seen one of these before? Well, this is a space jellyfish. And you've probably seen a lot of these recently because these come from Falcon 9 launches that have been occurring here from Vandenberg just after sunset. So what ends up happening is that up above us, the sun is still present, right? Sunlight is still there even though we're down in the darkness post-sunset. So what you're seeing is sunlight basically scattering off of the particulate of the exhaust coming off of the rockets. So this was a Falcon 9 launch back in 2018. The rocket up in the left there is the upper stage. That there is actually stage 1 coming back, and that's it firing its reaction control system thrusters to actually move or orient this first stage right there, which is just so cool to see that in action. But if you've ever wondered why do these things keep happening, it's because the orbits that these satellites have to go to require them to be launched at specific times, and sometimes those times just happen to be right after sunset. So that's where you get that from. So very spectacular. So keep your eyes to the sky. You never know when you might end up seeing a super fast space jellyfish happening with that there. Yeah. And speaking of space jellyfish, there was another one actually with a very small sat launcher from Vandenberg from Firefly Aerospace called the Firefly Alpha. They are really starting to pick up the pace in terms of their launch cadence. So it's really exciting to see their vehicle finally kicking things up and kind of getting in on the small sat market there. And I'm really looking forward to seeing more. We've had more launches at Vandenberg Space Force Base this year than we had from 1990 to 2015 combined.
Wow.
In just the past 8 months. So this has been wild. So if you really like to go watch rocket launches, Vandenberg Space Force Base is one of the places you could do that at. And I highly recommend you go up because you can get even closer than you can at the Cape. You can get within about 2.5 miles of some of the rockets that are flying out at Vandenberg, and you can be there. So, and there's the jellyfish that we got from that one. So.
And I went and saw Falcon 9 launch once. My favorite thing about it was the sound.
Yes.
It's like the sound doesn't come through in the videos. It just doesn't. The low bass, you can feel the rumble, that crackle. It's spectacular. It really is.
There's always this moment where everybody's like cheering at the launch, and then the sound hits and everybody gets quiet. And I think it's sort of like this very primal instinct kicks in that like, oh my gosh, I'm like witnessing this power that is indescribable, and I need to be quiet before it finds me. You know? Like it's almost like that prey instinct just kicks in, and you get really scared about it. So. Yeah.
Well, thank you, Jared. Very interesting.
Are the launches visible, by the way, during daytime and nighttime? Because here, obviously, we mostly see them at sunset when they were quite far away. But if you go up to Vandenberg or near it, can you just see any of them?
Any time of day, as long as it's not foggy, which that's always the roll of the dice. We jokingly call it Vandenfog for a reason. And they launch a lot of spy satellites there for a reason, too, which is because half of the time it's too foggy to actually see the rocket.
Nice.
In fact, once during a SpaceX broadcast, they're actually it was so foggy you couldn't see the rocket on the cameras when it was sitting on the pad, and they put a little graphic at the bottom that said, "The rocket is on the pad, we promise." So.
Yeah, exactly. Well, stay tuned, folks. More to come. Jared, you'll come on back and update us with all these updates we need.
Yes.
Starliner, does it get back? The Starship, all these things. So.
Yeah.
Well, now we're going to turn back to JWST wearing its Hubble shirt for us, and we want to talk about, has it broken cosmology?
No.
You see these sorts of things. Well, first of all, what is cosmology? What's it trying to do? Well, cosmology is trying to explain how the universe got here. And we do things like, well, we know we live in a galaxy, the Milky Way galaxy. And the Milky Way galaxy is in the local group. There's other galaxies around us. And that local group is on the edge of the Virgo cluster, which is a cluster of galaxies. Now, galaxies contain, well, anywhere from usually hundreds of billions of stars to trillions of stars. And then there's a gap, a space between them before you find your next little island that has hundreds of millions of stars. Now, galaxies can have gas. That gas can be turned into new stars, but not all of them are doing it. Sometimes they've run out of gas, so they just have stars in them. However, most galaxies have a big black hole in the center as well, in the very, very center part of them. Our galaxy has a 4 million mass black hole in the center. Black hole is an object that has so much gravity that light can't escape from it even. Nothing can get out of there. So you don't see the black hole, but you can see the effects of the black hole. Stars moving too quickly. As gas falls in, it'll shock and heat up and glow very brightly. So lots of stuff that can be seen. Well, this Virgo cluster has a black hole in it as well. It's in M87 in the big galaxy there. In fact, this is the Markarian chain. Here at Griffith Observatory, our big picture is of the Virgo cluster. You can see the Markarian chain. You can see M87, the galaxy that has the big black hole. We've even, the Event Horizon Telescope actually got a picture of both the black hole in our galaxy, Sagittarius A star, and the black hole in M87. So anyway, black holes exist, galaxies exist, and we have to figure out how to describe all of this stuff from a model. Cosmology has to say we need to make all these things, and they have to make it with the right structure. So in the top panel and on the left panel in blue, these are measurements of the locations of galaxies. So the distance away from us, our Earth is in the middle, our galaxy is in the center of this plot. And as you go away, you can see galaxies clump. They form these weird walls and they form these structures. Well, down below in red and to the right in red are models. Those are simulations where people took the information they needed, how much dark matter there is, how much baryonic matter, the normal stuff, how much dark energy there is, and then some of the other physical things you need to make the universe happen, things like inflation and all those things that go into it. You turn all that on, and you end up making structures that look a lot like what we see locally. You make galaxies, they make stars. Those galaxies have the right amount of stars. They're about the right size. They're making about the right structures. So we're happy about all of that. But we've never made measurements in the very, very early universe until now. The JWST, James Webb Space Telescope, is able to make measurements that are far earlier than we've ever made before, and we're starting to test things. And you're starting to see headlines like this. Yeah, Panic at the Discs. So actually, anybody know the band Panic at the Disco?
That's right.
Somebody out there does. So anyway, this is the scientists being funny, but they're saying, you know, rest frame optical observations of galaxy structures. So they're panicked. JWST is making them worried. Or has Webb broken cosmology?
Yes.
JWST is challenging our theories of the universe and finding things that shouldn't exist. Oh my gosh.
Oh my gosh,
They should-
science?
they
Science.
They should not exist.
Should not exist.
Should we exist?
I'm
No.
exempt. And then, Laura May, you're going to have to translate for
That's
us
right.
here.
I found these great headlines just to show also that the impact of this is really international. The first one says astronomers were stupefied or, astounded by the new discovery. Their jaws fell. The bottom one is similar. They're surprised and, again, astounded. And I don't know if you've met a lot of scientists, but I don't know that we're always the most emotionally effusive people.
I'm stupefied, I think.
Right?
My jaw.
Your
Just on the
jaw is
floor.
so on
I'm
the floor.
attempting to
So-
pick it up right now.
It's part
So-
of the new culture of media around this.
Yeah, well, media is using lots of terms to get the clicks. They think if we make these headlines that astronomers stupefied, confused, all these claims, I don't know. I'm excited by the results.
Yeah.
I'm an observer. I would have told the theoreticians long ago, the people running the models, that yeah, I know your models aren't going to be any good once we get the observations. Well, it's not that they're not good. They need to be revised a little bit. You change things slightly to fit the actual observations, or you need new physics. You might need some new physics in the early universe, and that's what we love. We love it when you need new physics because that's super exciting. So what are some of the observations that people are taking these crazy headlines and extrapolating? Well, here is a galaxy that actually this one isn't even that far away, but it was making stars, and then it just stopped. It made a bunch of stars in a burst, and then it stopped making stars. And you can see that little faint thing there. It's not very, very bright. It's not very big. This galaxy is known as quenched. And you can see here, this is the spectrum of it, but we should be seeing emission lines, lines that are sticking up out of that spectrum on the bottom, that black line. There are ones that go down, but there aren't any that stick upwards. In our own periodic table, we have some gas tubes that when they glow, you get emission lines, and you get an emission line spectrum. Well, when stars are being formed in a galaxy, you have a lot of glowing gas. You get emission lines. So we know this galaxy's not making stars right now because we don't see any of that glowing gas. So it's been shut down. But when did it make its stars? It had to have made them at some point. So we go back to that plot of the Big Bang, and on the left is the Big Bang itself. And then you got some physicsy things that happen. The inflation, I'm not going to explain what that is, but it has to do with the flatness problem, but I've never been a fan of it, but we need it. And then you make protons, you actually make some physical matter, and then things like energy and the particles will freeze out from one another. And then finally, you can see there the cosmic microwave background radiation. That's when the opacity drops low enough that light can flow freely. So all of a sudden, light is streaming. It's like the fog cleared in the universe. But then you hit this dark ages. And that's because the gas is too hot to make stars. It can't clump. It needs to cool off. So you have to wait. And you need to have the dark matter maybe help it clump. So you need time. And our physics says time has to go by. And then you make those first stars and those first galaxies. Well, that galaxy I was just talking about made all its stars where that yellow arrow is. It wasn't just making a first stars. It didn't slowly start making them. It made a whole bunch of stars right off the bat, right where they should be. And we think, well, that's a little fast. It's making the stars too quickly, quicker than we're seeing them locally. But maybe that's just something galaxies do in the early universe. Maybe. So it's a little bit of a weird one. So let's look at another galaxy. This one also has stopped making stars. It also has been quenched. But its stars, and they were able to get a spectrum of it that was a little more detailed. They used the Keck telescope, the big 10-meter mirror, in addition to the Webb results they got on it. And they were able to take a spectrum and see, yeah, there's not emission lines in it, but they were able to model it. And they were able to say, yeah, we need stars that had been formed all the way back then in the dark ages. That galaxy had to have made stars earlier than we thought stars could be made because we're seeing an aged population in there. And by an aged population, they're about 1 billion years old, 1.5 billion years old or so. So not old like 12 billion years old. Got globular clusters in the Milky Way that are 12 billion years old. Those are old to me. So when I was reading this paper, I was a little triggered because it was like they were calling them old stars. And I'm like, they're only 1.5 billion years old. That's not old. But for a galaxy that is in that part of the universe, that early, we're seeing it so young, that is old. It shouldn't have had stars that old. Maybe 600 million year old stars would make sense, not 1.5 billion year old. So it made a bunch of stars early on. It made a big burst. Probably a supernova or two went off, blowing the gas out, and that quenches that star formation. That's why it stops. That cold gas that you're making the stars out of gets blown out of the galaxy altogether. By the way, this thing isn't very big. These are like dwarf galaxy-sized things, the size of like the Large Magellanic Cloud. So these are not very big because big galaxies really haven't assembled by this time. The ones we're seeing are massive and they're bright, but they're not enormous galaxies. They're still kind of smallish, but they're bigger than we thought they should be. It's pretty strange. So weird stuff's going on, but it doesn't mean physics is completely broken yet. So Laura May, you have some too. Oh, you got a clicker. Good.
And
you found a couple too that were doing interesting things.
And there are some, in fact, a lot of this is so recent. That's the thing that's really great. A lot of these papers, discoveries have dropped really in the past couple of months, even some in the latest couple of weeks. So this was another great headline.
New paper just dropped.
New paper. Again, this was not from a paper, you know. I just want to clarify that this was not even really officially from any kind of the specialized media. This was just something on YouTube. But it's worth also that when you see all these things about, well, actually, you know, the Big Bang is completely disproven, et cetera, that's not true. In fact, you know, the James Webb has done nothing but confirm a lot of cosmology. A lot of it was correct. You know, none of that work gets to be thrown away. It's little fine tuning. And the cosmic microwave background is really the smoking gun for, you know, the Big Bang that we have. And it's pretty reliable, and we know all of this pretty certainly. We also know that the universe is expanding, and again, that's something we see. So most of it is, you know, when you see these kind of headlines, it's worth really thinking about it. There's also, you have to take into consideration the time that while this light is traveling towards us, the universe is also expanding. So you can, occasionally you will read things like, oh, but this, you know, this light is however many more billion years old, and again, you have to factor that in. It's not always that clear when it's presented in that way. So this is something that was actually found in 2016 by the Hubble Space Telescope. And this was part of our long tradition. We were talking about it earlier. You know, for the long time, we love records as humans, the furthest this, the brightest, etc. And so there have been, in fact, for a very long time, decades and decades, well, what's the farthest galaxy we can possibly find? And I appreciated your point earlier. You made a very salient point on, okay, well, but, you know, that's like saying the rocks. Oh, you know.
I found this big rock, and then I found a bigger one on my walk further along. It seems like I could always find a bigger rock.
Yeah.
Like there's always going to be a bigger one. Odds of me coming across the largest rock on Earth are small.
So the value, the value of these objects, it's not necessarily, oh, well, it's the oldest and it's the farthest, et cetera. That's not really, you know, the value is there is a scientific value to it when we find these objects because it tells us about the early universe. So that was one that was kind of a record holder for a while. It was found, like I said, by Hubble. I believe it's called GNZ11. Sorry, Z for the Americans. I don't know if you guys say Z or Z. Here's a close-up picture of this beautiful blob, right? And again, not to be, you know, we are so accustomed to looking at all these fabulous pictures of galaxies with these beautiful structures and all these images that Hubble brought us. And sometimes I think occasionally people may be disappointed when they see these kind of blobs, but they're fascinating and they teach us so much. And they're really stretching the limits of everything we can do. So I believe this one was, I think, at about 400 million, and that was found by Hubble, like I said. So it's also worth keeping in mind that James Webb, while it can see much more, it's also looking at a different wavelength. And it's not necessarily seeing that much further in time. It is seeing a little bit further in time, but Hubble, you know, it's not a throwaway telescope. We use it for still so many things. So this one, these were other candidates that arrived from the James Webb Space Telescope, and these were from a couple months ago for the farthest galaxy. And again, these are very red. So these are what we call redshifted. You know, the light has taken so long to travel to us, their light has been shifted towards the red part. And then here we have the JADES 4. This is the current record holder. This tiny little worm up there. So when we
well, the weird thing about this is two galaxies, though.
That's right. So on this in this arrow, you'll see. So there's actually that little red one right here. This is the bit that we're actually interested in. That one is from. So it's I believe it's a Z of 14.32. and I think it's estimated to be 290 million years old. 290 million years after the Big Bang that it formed, which,
Yeah.
I mean, that's just incredible,
Yeah,
right?
what-
That it,
cosmology predicted by the model we were using that stars just shouldn't be made then. It's too early. So that's why they're saying it's breaking cosmology. Well, no, it's not really broken. It means that we didn't have something right in it. We can fix it. We can patch it. We don't have to throw it away. So there's ways to fix this. It's just we need to know what actually was happening with the physics earlier on.
yeah. And this is, again, a very fresh result. So keep in mind that top portion, it's bluer. It is a cooler galaxy that is closer to us. It just happened to be in that field of view, so it's kind of overlapping it. But it's an incredible find. And, but in a month, in 2 months, they will probably have found another one that will also be just a tiny bit further. But it's remarkable the organization that we see. We are seeing clusters. We are seeing these organized galaxies. And like you said, there's also a couple things that are surprising about their stellar formation. But something that is worth keeping in mind, our own Milky Way, this is an image I shot in New Mexico, actually the best sky I ever saw in the United States, probably maybe on Earth even, just outside the Very Large Telescope, the Very Large Array. And that's, the Milky Way is not a fresh, what is the expression in English? Fresh chicken? Young chicken? No, I know there's an expression.
Spring
chicken.
chicken.
That's right. It's a spring chicken.
What's the French expression then?
I'd have to think about it, but it's nothing to do with chickens. But our Milky Way is no spring chicken. We estimate it roughly, it's always hard to pinpoint exactly, but it's about, we think it might have formed around 800 million years after the Big Bang. So if you compare that this record holder that we found is about 290 million years after, and the Milky Way is 800 million years after, again, so it's worth keeping in mind that all these incredible numbers, et cetera, we have seen galaxies forming for a while, and they may have different galactic processes of formation, right?
Yeah, well, it kind of makes sense. The Milky Way is not an incredibly large galaxy.
Yep.
These first things we're seeing forming in these JWST images might end up being sort of the central giant elliptical galaxies in clusters. We would expect those regions we're seeing that are the densest today would still be the densest regions very, very early in the universe, but they weren't as dense as they are now. The matter's flowed down into there. So you'd have one galaxy there, what's going to be the center of this cluster. So that's kind of what I'm thinking, that the Milky Way naturally should have formed later because it was off in a region that wasn't as dense. You wouldn't have formed stars right away. So that kind of fits in my mind.
In fact, there are even these galaxies I discovered called relic galaxies. I believe there's only one so far confirmed called NGC 1277 that is a galaxy that basically has had no interaction. And surprisingly, we find them in clusters, which is even more odd. And that one was found by Hubble. I don't think James Webb has found any yet. But this is an image, this is an artist representation just to show you an example of what an early galaxy could have looked like. So we still have, a lot of opacity in this gas, this kind of neutral hydrogen as these galaxies are forming kind of early on. And this is just to show you again a timeline of our universe and where everything is, sorry, Jared, and where everything is situated, that we have this kind of these dark ages. And then we're seeing really early on all these new star formation, things like that. And it's surprising, but it's not breaking cosmology. There's just a little bit of fine tuning.
I like to think maybe the dark ages were the dim ages, that you had little dim lights. You had small, galaxies that would become big, but the birth, these little baby galaxies starting to light things up. We expected that gas to get rapidly ionized by the massive stars, the big, giant blue stars. They have tons of UV. We expected those to ionize the gas, and that clears it out. That clears up the stuff, but I don't know. There's something else going on. There really is.
Yeah.
Like the gas hangs out longer, and the stars are still forming back there. So we'll figure it out.
We'll figure it out. And we have the potential for having also very massive stars that
Yes.
could have potentially only lived about a couple 100,000 years, which if you think about our sun, we've got an approximate, we're at about 4.5 billion years old, and it's got about that much left. So the difference in the lifespan, these stars must have been so enormous that they burnt out obviously quite quickly. after just a couple 100,000 years. So this one, this now, we'll talk about black holes a little bit because a lot of the discoveries that have been made also concern black holes in the early universe, the supermassive black holes. You mentioned them earlier, the images that we got from the Event Horizon Telescope, which are just incredible.
Yeah.
And so this one was that was a previous record holder, and that again formed at about, very shortly after the Big Bang, so 13.2 billion years ago.
This is a black hole?
So this was, I believe this was, yes, it was a supermassive black hole in this structure. But then we're going back to that little blob that I showed you earlier that was that very, very distant galaxy, the record holder found in 2016 by Hubble. And this is where we've had the latest discovery of a supermassive black hole, we think, again.
Yeah. We're seeing them due to the bright energy that's released as the gas falls in. So we're not seeing the black hole itself, but we're seeing the effect that as the gas gets close to it, it heats up and glows very brightly. We call them active galactic nuclei. Quasars are another name, but a quasi-stellar radio object was also one of these. So we're seeing the effects of them in these images.
And yeah, there's a lot of the interrogation is how they could have gotten so massive. For some of them, again, this early data that we're getting that shows them being absolutely enormous. Nowadays, the ratio, for example, in a galaxy like the Milky Way, we think we're at about 0.1%. The mass of your central supermassive black hole is about 0.1% the mass of the galaxy.
Yeah.
But in these early supermassive black holes we're finding, that is quite shifted. I forget the exact ratio, but some of them I think were almost 10% or even higher.
Yeah.
And how can anything form this fast? There are multiple ideas for how black holes form, of course. They're generally called, I think, the light seed and the heavy seed formation models. And there is a potential, again, not proven, never found, but for a direct collapse. So that is the idea that perhaps early on in the universe, a lot of this large amounts of gas could have, instead of gone through a supernova phase, where if we have these very massive stellar objects that eventually end their life, collapse on themselves and can form a supermassive black hole or just a black hole, what if we skip that stage and we just have a lot of this gas collapsing and directly forming a black hole, and then it is capable of, like you said, we have limits to how fast a black hole can actually grow. It's called the Eddington limit. But we're wondering if these feasting black holes could have started out so massive, and then we have something called the super Eddington limit, where they could have had these kind of bursts of accruing a lot of mass and, just doing that in these kind of bursts, and they could have grown very rapidly, but it is still a huge point of interrogation.
Yeah, it's not well understood how these grow that fast, but we know locally that the black hole mass does track the sort of bulge mass. Our galaxy has a big disk in it, but that's why we have kind of a small central black hole. 4 million solar masses is small. But you end up with like M87. It's, I forget, a trillion or something. It's enormous, but they scale together. M87 is all spheroid. So here we're seeing black holes that aren't following that relation. And we always wondered, did the black hole form first and then tell you how big that spheroid is going to end up? It's a sort of a predictor. Well, it seems to be that way. In the early universe, this relation isn't working. So we might be able to say, this black hole's this big. Well, you're going to end up with an elliptical galaxy or a galaxy about like this size. So it's kind of cool. But how did the black holes get that big to start? We don't know. Maybe they were even, some of them, primordial. Maybe they were formed in the Big Bang itself. We aren't sure. Again, this is all just conjecture.
And that's what's so exciting about the James Webb.
Yeah,
all of this, nothing's being broken. On the contrary.
Exactly. Here is this is you again. No wonder I'm like, what was going on here?
That's right. Although I forget exactly what this one. I'll skip this slide because I think this was another of the wide field. Oh, this was one of the wide
baby
fields.
Quasars. Is really what it is.
That's right.
It's another field that had lots of little quasars in it, and those are black holes that are feeding. So we're seeing a lot of small quasars that are feeding on gas at this really distant time, but they're feeding on gas kind of a lot. They're eating more than we thought they should. They're growing more rapidly than we thought they should have at that time. So we're seeing them all over the place. Now these ones, they're calling little
They're
red
calling
dots,
little
right?
red dots. It's nice, you know,
Yeah.
there's a lot of crossovers between dermatology, I feel, and astronomy. We've got sunspots, we've got little red dots. In fact, when I was Googling at one point to find one of their masses, and it was giving me all these dermatology things, and I was like, oh, that's right. So we found all these little red dots. And again, what we were talking about earlier, the light gets red shifted. So they've found a very large population of them. All these red dots out there. I don't know if you had anything to add about the red dots.
Well, other than the fact that we're seeing them in numbers that is confusing. We didn't expect to see this many of them this early in the universe at once. So it goes to show the black holes are already there, they're already eating the gas, and they're getting bigger. So how did this happen so early on in the universe? We're not exactly sure. The black holes have gotten big, they have access to this gas that's already falling into them. So things were much more active in the early universe at an earlier time than we thought. That's what this is all telling us.
And one of the earliest processes maybe, or something we're now finding, is high rates potentially of metallicity. Now metals, to add to the confusing things we have in astronomy, just like, you know, we have magnitudes that go in weird orders, we have populations of stars that go in this reverse order. Metals in astronomy is anything that's not hydrogen or helium, right? Our main component of our universe. So for us, that's our beautiful table of elements that you're seeing, where everything is a metal. But these are very important because, you know, with every new generation of stars, more of these metals are made by supernova, all of these, you know, very active stars that are seeding the cosmos and seeding the environments around them. And the potential for this is important because we could have had planets earlier than we may have thought recently. So in order to have, well, when I say planets, I also mean perhaps also rocky planets, right? So for now, we think that life, we don't really have any proof of life being on one of the gas giants around the solar system. So we have to kind of default to the idea that rocky planets may be a more hospitable environment to at least the types of lives that we can recognize. And so the potential for a higher amount of metallicity in the early universe is really exciting because it connects us to life, right?
Yeah, it connects us. So what we're seeing is that carbon, nitrogen, oxygen, these elements are being made at an earlier time than we thought they might be. And we're seeing them in not high abundance, they're not in large amounts, but they're in amounts big enough that maybe you could make rocky planets in that first billion years of the universe. We used to think maybe you need a little more time to go by. Maybe you even needed to have some white dwarfs form and collide because they actually make most of the iron and nickel. Some gets made in other types. Colliding neutron stars are needed to make things like gold and platinum and all the bling we like. So you need those dense cores of dead stars to make these things, and you're not going to have those at 500 million years after the Big Bang, at least not in great abundance. It's too early for white dwarfs. You've got none of them. They don't exist. So the fact that we're seeing these heavier elements to make rocky planets back then kind of makes me say, where are the aliens? As if you had rocky planets and you could make life after maybe only a billion years, well, they've got a 12 billion year head start on us. Where are they? So, you know, these are the questions we have. And we always wanted to know how common are rocky planets. Well, if you can make them that early on, they're much more common in our own galaxy then. We can find them around really, really old stars maybe, as long as there's just enough of these metals, which I love the fact that metals are anything like that. So, folks, that's our All Space Considered for you tonight. Thank you so much for joining us. Thank you, Laura May. Thank you, Jared. Thank you, Matthew and Paul. Thank you, Bill. Thank you, Victor. Thank you, Alan. Thanks to our whole crew that helped produce this show. All Space Considered is brought to you by Griffith Observatory, the City of LA, the Department of Recreation and Parks, and we always like to thank our nonprofit partner, Griffith Observatory Foundation. We hope to be back in the Leonard Nimoy Event Horizon Theater next month, where we're going to talk about Mars. A lot has gone on Mars. There's a lot of exciting results, and we're going to bring it all to you next month. So thank you so much for joining us this month, everybody. Thank you.